This is our second video for SLO 9, part 1, right? We're going to continue discussing the basics of hypothesis testing. And again, we're going to assume that the population standard deviation is known. Now remember, what we're really trying to do here is we're trying to figure out whether the accepted value of the population mean, mu, appears to be correct, whether the available evidence supports it. And then the question is there enough evidence to reject the null hypothesis or not? Right? So let's take a look at an example. Right? Let's just do another example, right? Here, we happen to know that the mean height for U.S. men is 69.4 inches. We randomly sample 300 men between ages 60 and 69 and get a height of 69 inches, right? And we want to determine whether the mean height for older men is less than the mean height for all men, okay? So what are the appropriate null and alternate hypotheses? Well, the null hypothesis is just immediate, right? That should just be I guess we could say the mean height mu of older men, and we shouldn't even say older, we should say men between 60 and 69, but we'll just say older men is mu equals 69.4 inches, I guess I should say. 69.4 inches, okay? What's the alternate hypothesis? Remember, for the alternate hypothesis, we need to read a little carefully, right? We see that there's this term less than, right? I'm going to highlight it. Less than the mean height mu. Let's write a better mu than that. Mu of older men is mu is less than, let me write that better, 69.4 inches. Right? Now again, where am I getting less than from? From the words less than, right? As given in the problem. They will always specify in the problem whether they're talking about less than, greater than, or not equal to. So be very careful to get the right alternate hypothesis. All right, now again, we're assuming unrealistically the population standard deviation is 2.84. Compute the value of the test statistic. Okay, now for the test statistic, let's see what they mean by that. What they really want is your z-score. So your z-score is going to equal x bar, well, oh my gosh, minus mu divided by your standard error, right? And that's going to be, I don't know, what is that going to be? 69.0 minus 69.4 divided by 2.84 over the square root of 300, right? And we can simplify this a little bit. Negative 0.4 over 2.84. Well, let me actually let me just get the standard error in the calculator. So I think that was 2.84 divided by the square root of 300. 0.164, let's say. 0.164. All right, so negative 4 divided by 0.164. What is that going to give us? Negative 0.4 divided by 0.164. Negative 2.44, okay. Equals negative 2.44. Okay. So at this point, we would, let's just do this old school using the book, and then we can go and use Minitab just to confirm. And we're going to state a conclusion. Let's see what we've got here. Remember, our z-score is negative 2.44, right? You see why I'm using this, right? Because there's a 0.04 right here. So we're right here. 0.0073. All right. So P equals 0.0073. which is less than alpha, which equals 0.01. Right, do we see that? See here I'm getting alpha equals 0.01. Right? So we reject the null hypothesis that mu equals 69.4 inches, right? So older men likely are not as tall, or maybe I'll say are likely, I should be a little more specific than that, have mean height, goodness, less than that of men. Okay. Now, how would we do this in Minitab? It'd be a little bit quicker, I suppose, because we don't have to calculate the test statistic, right? But of course, they asked us to, so we kind of need to, right? But anyway, basic stats. One sample Z. The sample size was 300. Sample mean was 69. The known standard deviation, I want to say it was 2.89. Was that correct? No, 2.84. See, glad I looked. 2.84, perform a hypothesis test. The hypothesized mean was 69.4 inches. Now, for the confidence level, we're going to do 99, right? Because that's 1 minus the significance level. We want to make sure also that we're mean less than, actually, sorry, one sec. I wrote 99. That should be 0.99. Also make sure the mean is less than the hypothesized mean, right? Right, and sure enough, we get the exact same thing. You see that? Let me just take a quick picture of that. Again, and, just, sure enough, I just want to point out that we got the exact same thing. I put that 99% upper bound. Don't worry too much about that. Well, I guess that's somewhat useful. Maybe I'll just keep that here. You don't need to worry too much about it. But anyway, we'll just, I'm just going to paste this right here. Shrink that down a little bit, and maybe a little more. Right, and sure enough, we get the same thing, okay? So however you want to do it. All right, anyway, continuing on. Note that, again, I call this HA, but I really should have called it H1, H1, H1. Down here also H1. My bad about that. Right, you can call it HA if you want, but book and Minitab call it H1. All right, anyway, note that the alternate hypothesis stated the height of the older men was less than 69.0 inches, right? When it states that it's less than the value in the null hypothesis, our hypothesis test is a left-tailed test. And of course, if it's greater than, greater than the value, our hypothesis test is a right-tailed test. I should also say if H1, right? Oh, never mind. I won't state that yet. We're going to do an example, okay? Okay, so now let's look at this example, and we're just going to use Minitab. It's a little quicker, right? So we're calibrating a scale, right? We're using a weight that's somehow known to be exactly 1,000 grams, right? I guess whatever scale weighed that was super calibrated, or they used science, or whatever. Anyway, they weigh this weight on the scale 50 times and read the result each time. The 50 readings had a sample mean of that, 1,000.6. Now they say the scale's out of calibration if it differs from 1,000 grams, right? Statistically significantly differs, right? And so we want to perform a hypothesis test, right? So what are the appropriate hypotheses? Well, H naught is going to be the scale is properly calibrated. So the mean is the mean weight, really, like if you were to weigh this thing a whole bunch of times, it would be 1,000 grams. Okay? Alternate hypothesis. Be a little careful here. The scale is not properly calibrated. So population mean does not equal 1,000 grams. Now again, this is not greater than, this is not less than, this is just not equal. How did I get not equal? I got it from the word differs. Differs just means that it's not the same as. In either direction, it could be too high, it could be too low. So that's what we're going to write, okay? So anyway, we know that sigma equals 2, right? Compute the value of the test statistic. So at this point, let's just use Minitab, right? It's a little quicker. Stat, basic stats, sample Z, sample size. Now, what would the sample size be here? It's going to be 50, right? Because we weighed the weight 50 times. The sample mean was 1,000.6. The known standard deviation is a nice and even 2. Beautiful. What was the hypothesized mean? It should be 1,000. And now here, what confidence level did they want us to use? 0.05. Okay. So 0.05 means 0.95 confidence level, right? And here we're going to make sure that we do mean is not equal to the hypothesized mean. All right, and that's our answer. Right, just in case they asked for any kind of test statistics, blah, blah, blah. Forget that. We won't do that. Okay, we just got that, we got that, we got that. And we will paste this right over here. Okay. Actually, I guess they wanted the test statistic for B. So we'll just say Z equals 2.12. And then I guess we'll say P equals 0.034. Which, by the way, is less than alpha, which is 0.05. Okay? So reject the null hypothesis. So the scale likely is not calibrated properly. Okay? Now note that in this example, right, this stated that the mean weight did not equal 1,000 grams. When the alternative hypothesis says that mu does not equal the value of the null hypothesis, our hypothesis test is a two-tailed test. Okay? Right. Now, by the way, the reason that we have left and right-tailed tests, the reason we call them that is, let me actually draw this in red, make this pop, right? What is really happening is that we have our hypothesized mean, right? And in a left-tailed test, we get a sample mean that's less than that, right? That's our x bar. And we want to see what's the area under the normal curve, really under the sampling distribution curve, right? What is that area? That area right there is our p-value, right? And the question is that area smaller or larger than alpha? Okay. Now, of course, the right tail test, right? Exactly the same thing, just the other side. Right, we've got our mu. Let me just move this up a little bit. Maybe move this up a little bit. Oh, maybe move this guy a little bit. This is just a little bit. There we go. Anyway, here's our mu. Here's our x bar. Right, and then the question is, right-tailed. Right, get it right there. Okay. That right there is, again, our p-value. Okay. With a two-tailed test, same sort of thing. It's just that, it's a bit of both, right? Right, we've got mu over here, and either of these could be our sample mean. But here we've got it like this. Actually, let me instead, this might be a little, no, I'm going to leave it like that. That's sort of okay. Yeah. Actually, no. I'm going to change this a little bit. Not that it's wrong, but just to be clear, you could also think of it like this. You could think of it as there's alpha, or there's our z-score, there's a test statistic, and we want to see whether our sample statistic is, over here or not. Right, and actually I guess you could say then that, like, that's our p-value. That's our p-value. Right, and alpha, for example, might be over here. Our p-value might be over here, for example, like it was in this case. All right, anyway, moving on. When we reject the null hypothesis, we're not saying that it's necessarily incorrect, but we are saying that the evidence, maybe strongly, suggests H naught is incorrect. Right? Now, even though the evidence is on our side, there is a chance that the null hypothesis is in fact correct. Now, one thing we really try to avoid is rejecting the null hypothesis when it's correct. Right? Rejecting the status quo is a big deal. We want to make sure that there is strong evidence on our side to do that. All right? But if it happens that, in fact, the null hypothesis was correct and we were incorrect, and we were, I should say, maybe we were just, and I'll say we were incorrect to reject the null hypothesis, the error of rejecting the null hypothesis when it's in fact true is called a type 1 error. It's bad to commit a type 1 error. We try to avoid it. That's why we have such a strong level of significance, right? The probability of a type 1 error is alpha, the critical value. Okay. And just a little illustration of what's going on here, right? This right here is alpha. Okay. Now, analogously, if we fail to reject the null hypothesis, we're not saying for certain that it's correct. Rather, we're saying we don't have enough evidence to reject the null hypothesis, right? Remember, there's a high standard for evidence to reject the null hypothesis. You could have some evidence that it's not correct. Maybe I should say that yeah, I guess I'll just say to reject the null hypothesis. That's fine. Okay? So even though the evidence is on our side, but sometimes it does happen, right, where, like, maybe more than likely it happens, where the null hypothesis is in fact false, and we were, or I should say maybe not false, I should keep the same thing, incorrect, and we were incorrect to fail to reject. Oh, I guess I'm saying false right here, so I guess I'll call this false. And I guess I should say that H naught is in fact true. Sorry about that, guys. Okay. So the error of failing to reject the null hypothesis when it's in fact false is called a type 2 error. Okay? Now the probability of this is called beta. We're not going to get much into beta. I'm going to super quickly sketch out what beta looks like. Try that a little bit better. If this is the sampling curve about the expected, about the null hypothesis mean, and then you have another curve around the true mean, then this right here is the probability that we were wrong to do so. Or actually, sorry. Whoop. Sorry. This right here is the probability that we rejected H naught, right? And we're, sorry, that we failed to reject H naught, but it's actually false. It's beta. We're not going to get much into that, but just so you know, that's what beta is, okay? All right, let's do one more quick example. Here are null and alternate hypotheses, sample size of 48, sample mean 12, standard deviation 6, right? Population standard deviation 6, right? Let's just do this, right? Enter our stuff into Minitab. Get this going. Stat basic stats on sample Z. Sample size, what is the sample size? 48. Sample mean, 12. Standard deviation is 6. Perform the hypothesis test, absolutely. 14, right? And then note that the alternate hypothesis is that, right? Now, we'll keep the confidence level at 0.95, because we're looking at an alpha of 0.05 value. Anyway, we wind up getting Z value and P value accordingly, right? So let's just get that real quick. That real quick. Get that in there, get that in there, get that there. And let's see what we've got. Get out of here. All right, so there we go. So part A, compute the test statistic. All right? That's our test statistic, okay? Is H not rejected at the 0.05 level? No, since P equals 0.021 is, oh, sorry. Yes, sorry, I lied. Yes, since it's less than alpha, which equals 0.05. However, no, we do not reject the null hypothesis at the 0.01 level, right? Greater than or equal to whatever alpha equals 0.01, okay? So that's what we do.